This lesson is all about the first law of thermodynamics, something you need to know about what happens to gases as they compress or they expand. And it all stems from, as I said before, the law of conservation of energy. It's the idea that energy cannot be created or destroyed. So the whole idea is that when you add energy to a gas, it manifests as the kinetic energy of its particles, which then means it manifests as its change in temperature. So I'm going to show you again, I apologize for those of you who've seen this before, two short videos which demonstrate this rather well. So if I share my screen, then I can show you two particular effects that you'll come across. It's having a bit of a salt. There we are. Okay, so we've got the first one where we've got a sample of gas and it's going to be compressed rapidly. This is what we call an adiabatic process because we have no time for thermal energy to go in or out of the gas in the middle here. So we're going to see what happens when work's done on the gas. You can see that as you compress the gas, its temperature increases. In fact, increases enough to ignite that little bit of cotton wool that's in the middle of it. So when you compress a gas, it heats up. There's a very similar effect that you get if you allow a gas to expand, which this lecturer that I've selected will show you. Have I lost Zoom again? Bear with me. Right, I think I'm back in again now. I'm not sure if this is going to work or not. So I had a little bit of a pause there. Our computer seems to be going a little bit slowly at the moment. So the whole theory, the theory we got to was that when you compress a gas, it heats up. And I'm just going to now show you what happens when a gas expands.
And so when the air expands, then the air cools. HC. I got a demonstration for you all to try right there at your seats. Are you ready? Everyone have a hand? Put your hand in front of your mouth and with your mouth open, so when you breathe, so the air doesn't expand, I want you to blow. Okay. Now bring your mouth down really tight so the air expands when it comes out. Notice any difference in temperature? Okay, you want to see that more dramatically? Watch this. There's some steam here, huh? Would I dare to take this glove away? Yeah, easy. Easy city, man. No problem. Hot or cold? Begin with a C. It's cool. Relatively cool. HC. I'm not going to put it way down at the nozzle. It turns out that which you are seeing here, gang, is not steam. That which you can't see, that's the steam. But what does that steam do? Begin with the X. Expand. And when it expands, what's it do? Begin with another C. Cool. And there's your evidence of it right there. Isn't that remarkable? Okay,
so that's your basic idea. So what is that all about? Well, in order to do that, I need to go back to my piece of paper here. So where does it link? Well, the idea is that if you think about it, if you've got the internal energy of a gas, a change in internal energy, which is going to be a change in temperature, Well, that is actually equal to two particular things. The first one is to do with the thermal energy supplied. And this is what we often think about when we're heating things, where because when you heat up, it says that when you heat up a gas, its internal energy increases, which means its temperature will increase. But there you could see an extra effect. You could see the idea that with the first demonstration, with the first piston, when they compressed the gas, they applied a force, and they moved that plunger a distance. And we know that when you apply a force and you move a distance against that force, we know that that is work done. Now we've got to be careful. That's the work done on the gas. Okay. Now, if you think about it, what that actually means is that if that's the work done on the gas, the second experiment, the gas expanded. So as the gas is expanding, it's applying a force on the atmosphere. As it's applying a force on the atmosphere and moving a distance, the gas is not having work done on it. Work is being done by the gas. So we now know that for expansion, we know that work is done by the gas. So W, that W part of the formula here, that's negative. If you think about it, if work is done on the gas, you're putting energy in, which is why its internal energy will increase. If the gas does work on the atmosphere, so the gas is applying the force there and it's moving against, and it's moving in the direction, so it's expanding, then the work is going to be done by the gas. So energy is being taken out of the gas. So that W value becomes negative. And that's the basic idea behind the first law of thermodynamics. There is a way there is a way of actually calculating that work done. If you think about it, if we're logical, we can actually say, well, if that's the case, we want to work out the work done. We know that the work done on a gas is equal to the force. In the case of the first demonstration, it was the force pushing that plunger down to compress the gas, multiplied by the distance moved against the gas. Now, obviously, it's difficult to just talk about force, but remember that force is related to pressure. So if we think about it, if we've got our cylinder of gas, I'm going to draw it on its side, it's easier to display on the screen. If you imagine you've got a cylinder of gas, okay, and you've got in there your plunger. There it is. Okay. Now, what you could do is you apply a force in that direction, and we know that gases, unlike liquids and solids, will compress. So the new position of the plunger would be here. So you've moved a distance x. So we've got to think about this very, very carefully. What we need to really say is that if that happens, well, we've got force times distance is the work done. But the trouble is, it's very hard to think about it in terms of forces and distance. So what we've got to do is we've got to think about it in terms of pressure and volume. So that's the x. Well, how much has the volume changed? Well, the volume has changed, delta V, by the distance x multiplied by this sort of cross-sectional area of the plunger. Okay, and that makes sense. How do we work out the pressure? Well, the pressure is the force divided by the area. Okay, so if we just rearrange it to make expressions of x, so x is equal to delta V over A, okay, and F is equal to, have I got that right? Yeah, And F is equal to, well, it's pressure times the area. I'm just going to put that underneath so it's more convenient. We then will work out the work done is simply, well, if it's force times distance, that's F times X. So we just substitute the expressions. P times A gives you the force, pressure times area, and X gives you delta V over A. So that's the change in volume divided by the area. And I think anybody can tell straight away that the areas cancel, okay? Because anything divided by itself is just 1, anything multiplied by 1 is itself. And so we end up with the work done on a gas is equal to, well, it's pressure times the change in volume. To apologise, there we are, which equals the work done. Okay, which is in meters cubed. So that then is how you can calculate the work done. So what does this really mean in real terms? Well, there's lots of different examples for this. The first one is we now know that if you make a gas expand rapidly, okay, that work done is negative. And if Q equals 0, now Q means the added thermal energy. That's energy you actually add by heating or take away by cooling. Okay, there's no conscious adding or cooling because it's a very rapid expansion. It hasn't had time to happen. So if that Q is equal to 0, it's what we call an adiabatic process. Then the change in the internal energy is equal to 0. Now, as it's W, it's minus the work done by the gas, okay, due to rapid expansion. So delta U is negative. And the gas cools, okay? That's why if you blow on your hand with a very, very fine jet from your mouth, you'll find that it will feel cooler. It's a very, very small effect, much greater if you're using something like a fire extinguisher. You fire off a fire extinguisher, the gas expands very, very rapidly. And because it expands very rapidly and does a lot of work on the atmosphere, it cools down to very, very low temperatures. And that's why, again, some aerosols also, when you use an aerosol gas from a spray can, sometimes it can feel quite cold, okay, because the gas has expanded. It's also the reason why when you inflate tires and on a car, the air feels hot afterwards, because you've done work on the gas to compress it. And that's why tires sometimes get hot when just after they've been inflated. There are lots and lots and lots of different examples of that first law of thermodynamics. There's also a very strange effect in which if you take something like just trying to think what this was. If you take our weather systems, as the air is compressed and expands, it actually does change the change the temperature. One of the other things is that when you do specific heat capacity, and this is just an aside, you'll come across this, the thermal energy supplied to a substance is equal to the mass times specific heat capacity multiplied by a change in temperature. For a gas that works, but actually what you've got to do is, for a gas, you remember that a gas expands. So if there's no expansion, that works. For an expanding gas, it's actually the energy supplied to raise its temperature plus the work it does on the atmosphere as it expands. So if you just take an ordinary gas and you heat it up, its temperature might not increase as much as you would expect because it's expanding and doing work on the atmosphere around it. So those are the basic concepts surrounding the first law of thermodynamics. It's quite an interesting concept, and it does tell you a lot about things like how refrigerators work, how compressive heaters work, and also explains how diesel engines work. If you think about it, with a diesel engine, diesel engines don't require an ignition. What they do is the piston compresses the gas. It does work on the gas, which is a fuel and air mixture, and it makes the gas hot enough to ignite the diesel fuel. And that's how diesel engines work. That's why they sound a little bit different to petrol engines. So that takes us pretty much to the end of the lesson, the end of the talk bit of the lesson. Does anybody have any questions?
No.
Any questions at all?
Is this is recording, right? Like,
yes,
you post it.
Yes.
Okay.
Yeah. I'm going to post the recording as soon as I possibly can. I apologise for the bit of a wobbly start. My computer crashed about halfway through. Well, about two or 3 minutes into the initial attempt at running the lesson. So what I'll do is I will save this recording and I'll post it up on Show My Homework for you to download and watch at your leisure. What you need to do, well, there's several little things to do today because you've got 3 single lessons. You've got 3 45-minute periods. You've got your double today, and then you've got a single in the afternoon as well. What you need to do is really just make sure you've watched the video, understood what I've just told you, but also go on Seneca Learn. I've created a link for Seneca. You go on there and do the exercises. That will reinforce what I've shown you, and then have a go at the UFP exam style question, which is your submissible bit of work ready for tomorrow. What I'll do tomorrow is I'll take you through a walkthrough of a past UFP question on gas laws. We're coming towards the end of the topic now, so I'll take you through the UFP questions on gas laws, and I'll get you to then have a go at doing them with a view to next week maybe doing a little bit of a test on your own using your knowledge of gas laws. Okay. Any questions? Anything at all?
No. Maybe no question.
Okay. So what I'll do is I'll stop right there, and have a go at the tasks. It's the reminder for it is all on Show My Homework. So please make sure that you do go and Show My Homework so that you know what to do and submit your work via Show My Homework. All right. I'll see you next time. Bye.